Cultivation Architectures. Episode 7. Mineral Nutrition and the Language of Uptake. Every cultivation architecture eventually collapses into the same biological reality regardless of method, medium, philosophy, or level of control. It doesn't matter whether the system is soil, coco, rockwool, perlite, peat moss, hydroponics, or aquaponics. Every system converges at a single interface where plant roots interact with dissolved ions in water. At that interface, cultivation stops being about inputs and becomes entirely about electrochemical behavior, transport regulation, and internal biological demand. The plant does not recognize nutrients as products, formulas, or categories. It responds to ions, gradients, water movement, charge relationships, and its own internal requirement to maintain stability under changing conditions. Mineral nutrition is not one part of cultivation. It's the underlying operating system beneath all cultivation architectures. At the foundation of this system is the full requirement set of 19 essential elements, each contributing to a different layer of plant structure and metabolism. Carbon, hydrogen, and oxygen form the structural backbone of biomass and are sourced from air and water. Nitrogen, phosphorus, and potassium regulate growth, energy transfer, and metabolic expansion. Calcium, magnesium, and sulfur provide structural integrity, chlorophyll function, and enzymatic activation. Iron, manganese, zinc, copper, boron, molybdenum, chlorine, and nickel operate as catalytic regulators controlling thousands of enzymatic reactions that define metabolic precision. These elements are not independent inputs. They form an interconnected system where balance, ratio, and interaction determine biological outcome far more than absolute quantity. Within this system, nutrients are divided into mobility groups that determine how deficiency patterns appear in plant structure. Mobile nutrients such as nitrogen, potassium, and magnesium can be relocated internally, meaning the plant actively redistributes them from older tissue into new growth under deficiency conditions. Immobile nutrients such as calcium and boron cannot be effectively relocated once deposited, meaning deficiencies appear immediately in new growth and structural tips. This creates a diagnostic system that is not linear but hierarchical, where symptoms reflect internal prioritization rather than simple absence. At the root interface, nutrient uptake is governed by membrane transport proteins that regulate ion flow based on internal concentration, external availability, and metabolic demand. This is not passive diffusion. It's an active biological selection process where the plant continuously evaluates its internal chemistry and adjusts uptake behavior in real time. Calcium uptake slows when internal sufficiency is reached. Potassium uptake increases during high metabolic demand, and nitrogen uptake shifts depending on growth phase and enzymatic activity. This means nutrient availability is never absolute. It's conditional, based on physiological context. One of the most important structures in mineral nutrition is the interaction between cations and anions, which forms the electrical backbone of plant nutrient balance. Cations such as calcium, Magnesium, potassium, and ammonium carry positive charge and influence structural and osmotic behavior. Anions, such as nitrate, phosphate, sulfate, and chloride, carry negative charge and regulate energy transfer and metabolic cycling. The plant must maintain continuous electrical neutrality, meaning uptake of one group directly affects uptake of the other. When this balance is disrupted, competitive inhibition occurs where excess of one ion suppresses uptake of the other, producing multi-layered deficiency patterns rather than single point failures. This is where nutrient ratios become more important than elemental concentration. The plant does not respond to isolated values. It responds to proportional relationships. Calcium to magnesium balance influences structural integrity and enzyme stability. Potassium to calcium balance influences water regulation and cellular expansion. Ammonium to nitrate balance influences pH drift, metabolic efficiency, and root zone stability. These ratios define system behavior more accurately than any single EC or ppm reading. Electrical conductivity measures total ionic concentration, but not structural composition. Two nutrient solutions with identical EC can produce completely different plant responses depending on ion distribution. EC describes intensity of dissolved salts but provides no information about functional balance or antagonistic relationships. It's a macro indicator, not a diagnostic system. pH operates as a chemical control layer above this entire system. It determines nutrient form, solubility, and availability. Even minor shifts in hydrogen ion concentration alter precipitation dynamics, ion stability, and uptake accessibility. In hydroponic system, this effect is immediate due to absence of buffering. In living soil systems, pH shifts are moderate through organic matter, microbial buffering, and mineral interactions. Coco systems provide partial buffering through cation exchange capacity while still requiring active control. Rockwool and perlite behave closer to hydroponics with high responsiveness and minimal chemical buffering. At the root zone, none of this is experienced as numbers. It is experienced as flow, pressure, and gradient movement. Water enters the plant based on osmotic pressure differences created by the dissolved ions. This is where mineral nutrition becomes physical biology. When external ion concentration is balanced, water moves steadily into the plant, supporting stable turgor pressure, consistent expansion, and efficient metabolic function. When external concentration becomes too high, osmotic pressure reverses, restricting water movement and forcing the plant into protective regulation states where transpiration is reduced and stomata closed to preserve internal balance. This is commonly interpreted as nutrient burn, but at the system level, it is osmotic overload caused by excessive ionic density. When external concentration is too low, osmotic pressure weakens, allowing water to enter easily but reducing ionic density requiring for metabolic function. The plant becomes hydrated but chemically undersupported, leading to weak structure, pale expression, and reduced metabolic intensity. This is underfeeding at both osmotic and biochemical levels at the same time. Both overfeeding and underfeeding are not separate phenomena, but opposite expressions of the same regulatory system imbalance. Osmotic behavior shifts throughout plant development. During early growth, the root system is underdeveloped and transport capacity is limited, making it sensitive to high ionic concentrations. Lower EC environments promote stability during establishment. During vegetative growth, osmotic demand increases significantly as transpiration rises, root mass expands, and metabolic output increases. The plant can now handle higher ionic strength because transport capacity is fully active. During reproductive or high metabolic phases, osmotic regulation becomes more sensitive again, not due to reduced capacity, but due to increased metabolic load and tighter balance thresholds. This is why feeding strength cannot be treated as a fixed value. The same EC produces different outcomes depending on plant size, root health, environmental stability, and developmental stage. Nutrient concentration is not a static target. It is a dynamic relationship between external solution strengths and internal transport capacity. Environmental conditions are inseparable from this system because they directly regulate osmotic behavior and uptake efficiency. Temperature controls enzymatic activity and metabolic speed. Humidity controls transpiration pressure and water movement. Oxygen availability in the root zone determines transport efficiency. Carbon dioxide influences photosynthetic demand, which feeds back into nutrient uptake requirements. Every environmental variable ultimately converges into mineral transport efficiency and osmotic regulation. Across all cultivation architectures, mineral nutrition behaves differently, not because the plant changes, but because each system modifies how ions are delivered to the same biological interface. Hydroponics provides direct ionic availability in solution. Living soil generates ions through microbial decomposition and organic cycling. Coco mediates ions through exchange sites and buffering interactions. Rockwool and perlite provide uniform physical delivery with minimal chemical interference. Aquaponics generates ions through continuous microbial conversions within a living aquatic ecosystem. Despite these differences, all systems converge at the same regulatory interface, the root membrane. This is the final point where external design becomes internal biological response. Everything before this is system architecture. Everything after this is plant regulation. Biological and functional additives operate within this system, but do not replace it. Kelp introduces hormonal and signaling compounds that influence stress response and developmental regulation. Amino acids reduce metabolic energy cost by supplying preformed nitrogen structures that bypass synthesis demand. Humic and fulvic acids improve chelation nutrient mobility and uptake efficiency by modifying ion availability in the rhizosphere. Silica strengthens structural integrity, improves water regulation, and enhances stress resistance through cell wall reinforcement. These inputs do not define nutrition. They modify system efficiency within the existing mineral framework. When all this is understood, mineral nutrition stops being a feeding strategy. It becomes a continuous electrochemical regulation system where ions, ratios, transport capacity, osmotic pressure, and environmental conditions interact all together at the same time to determine plant performance. The objective is not to force nutrients into the plant. The objective is to maintain a stable operating environment where the plant can regulate its own internal chemistry with minimal resistance. And at that point, Mineral nutrition is no longer a subsection of cultivation. It becomes the universal language that every cultivation architecture is built on, whether it is recognized or not.